So the next speaker is Daniel Ferris from University of Florida, and the talk is on comprehensive psychological assessment of human-robot interaction.
Okay, just checking. Megan, can you see my screen okay?
Yes.
Good. Okay, so I'm going to talk at a higher level, 10,000 foot sort of level of the field, and I'll try to answer your two questions that you had, Megan, earlier. Number one, we've come a long way from where we were 50 or 60 years ago. When you look at, the initial plans of what people envisioned for having robotic exoskeletons, these are two of the first versions that were out there. And the first working version that I know of was Hardyman, which was in 1969. So, a good 50 years since. We've made a lot of progress over the years. And when you look at the range of different devices that are out there, two of them that I'll talk about are the Onyx from Lockheed Martin and the Exoboot from DeFi. I would argue the hardware is really where we've made the biggest improvements. We have much smaller, more powerful actuators. We have better materials, carbon fibers, titanium. There's an awful lot of things in the hardware that have come a long ways. And to a certain extent, I think that actually highlights the negative side, which is we still have a long way to go in the controls. We don't have the control figured out, and we need a lot of work to get it done. I also take this chance to take anything I say about these exoskeletons with a grain of salt, because I do work with the devices from Lockheed and DeFi, and want to disclose that right away. When you start thinking about how do we evaluate helping, and I'm going to focus a lot on human locomotion, lower limb, and there's a couple of reasons. Number one, it's most of my experience, and the reason it's my experience is the upper limb is really, really hard. There's a lot more degrees of freedom. There's a lot more precise position control. It's a difficult situation to try to build robotic hardware to assist with. The legs are a little bit simpler. There's fewer degrees of freedom. It's more of an impedance control situation. You're trying to prevent yourself from falling. We have a lot of working robotic interventions. I showed you two, but there's another 40 out there that you can actually buy or test that can assist with human locomotion. We need to evaluate them, and how do we typically evaluate them? And the number one method has traditionally been metabolics. Let me measure how much oxygen you're consuming. Let me measure how much carbon dioxide you're producing. I can therefore measure how many calories you're burning and see if this device is helping you reduce the calories while you're walking on a treadmill in a lab. And while I'm not going to say that it's not a good thing, I know that humans do decrease their metabolic cost and try to optimize energy expenditure by changing the way they walk. But in the real world, it's not the only thing. And so we need a lot more measures out there. We can't rely on a single gold standard. Oh, if this is what it does, then it helps. No, it can't all be on metabolics. There are simple ways people can film them to do kinematic analysis of their motion patterns. You can have them walk on special force platforms or force measuring treadmills to measure their ground reaction forces. And when you combine the kinetics with the kinematics, you can get inverse dynamics and start to look at joint torques from the muscle standpoint. You can also put electrodes on the skin and record the muscle activity beneath the skin. You can go a little bit farther if you want. Probe the nervous system, see how the spinal cord reflex loops are changing by actually stimulating nerves and measuring reflex responses like the Hoffman reflex. That can provide a lot of insight to trying to identify how the nervous system is adjusting to what's going on. And then more recently, we and a number of other labs have developed ways to actually do measurement of electrocortical activity, EEG, while you're walking with exoskeletons and devices, so that you can actually get insight on a millisecond time scale as to what's going on into cortical adaptation. And I think we really need to take advantage of all of the different possibilities available to us because trying to identify what works is not solely dependent on metabolics. Metabolics has its point. So here's an example of testing a knee exoskeleton, walking on the level and walking incline. This was work by Mary McLean, a PhD student in my lab, not too long ago, just published, trying to evaluate if we provide mechanical assistance, can we reduce energy cost? And the idea is, well, we know we're helping out at the knee. The knee mechanically doesn't do a whole lot on the level, but it does more work when you start going incline. It's a relatively larger percentage of the workload walking uphill with a backpack than it is walking on the level without the backpack. And lo and behold, yes, the evidence shows that if you're actually going to carry a heavy load up a hill, the exoskeleton helps, and it provides assistance at the knee, reduces your metabolic cost. But unfortunately, on the level and without the backpack load, it really doesn't save you energy. It's more just getting in the way. And that's an example where metabolics is very helpful. It tells you that there are certain tasks and environments where it is helpful, and there are other tasks and environments where it's not as helpful. When you start to deconstruct what humans are doing when they move their bodies, traditionally, there's a threefold way to look at human performance. One is the biomechanics, looking at the mechanical dynamics of what's going on. One is the metabolics, like we've talked about, evaluating how much energy they're using. And then the third part is the motor control. How are they actually using their nervous system to activate the muscles, control the mechanics, to burn the energy in a productive way? And that's been very useful to us for 100 years in terms of studying human motion and performance. When we move to actually looking at human and machine together, we have been adopting the same sort of strategy where you need to understand the mechanics of the interaction between the machine and the human. We're looking at the energetic cost, not only of the human, but how much energy the device is burning through. Batteries are getting better all the time, but they're still finite. You can't have a system that's going to burn through an awful lot of energy in a short period of time. And that was one of the problems with Sarcos's exoskeleton. It has very powerful actuators, but the amount of energy needed to supply it was just too high of a drain. The control is really the aspect we're still working on, and most of the presentations in this workshop are really focusing on is how do we figure out what the human intends, how do we translate that into something that the machine can understand, and how does we control the machine so it's safe for interacting with the human. I don't want us to abandon this approach of mechanics, control, and energetics, but I think there are under-talked about and underserved ways to look at human-machine interaction. And so the second question that you had, Megan, is what really needs to be done? I would argue that we need to look at another 3 parameters. And one of them, energetics, I would call the same. Really no translation. Energetics is a good way to evaluate what's going on, but we need to evaluate agility and embodiment. And some people would argue agility and stability are just different axes of the same parameter. When you have reduced stability, you can become more agile because you can change your direction. And as you have much more stability, you are not perturbed by external forces, but on the same point, it's harder for you to change direction. This plays out in the design of airplanes. When you have a very stable plane like a glider, then it's not going to be perturbed by external forces, wind gusts. But on the other hand, it's not as agile as if you have vehicles that lower on the stability list and they're designed to change direction at a very quick pace. And so the 2 things I'm going to talk about really are agility and embodiment. How do we measure them and why they're important? So let's talk about agility. We're not going to get agility walking flat level surfaces on a treadmill. So this is us doing analysis of the DeFi exoskeletons. That's great. But these devices are intended to work out in the field. And one way to do this is to actually take them out in the field. So can we measure how devices are working when you're going over natural terrain on a hike? Or even in an urban setting, if you have to navigate by having a sudden jump, instead of a steady state rhythmic stepping pattern, all of a sudden you need a acyclical sort of burst of energy. How is that helping you get over a puddle in an urban setting? How does it work when you deal with different types of terrain, from whether it be grass or whether it be pavement. And what happens when we have obstacles and moving obstacles? If you're in a crowded subway, you're not going to walk the exact same pattern step after step after step, because you have to dodge left and right and go up and down stairs and deal with the obstacles that you're confronted with in both natural and urban settings. This has long been known by people that work in bipedal robotics or legged robotics. Here's an example from Jesse Grizzle's lab. They're trying to evaluate how well their control works, and so what do? They take it out onto different types of terrain. They need to see, are we agile enough to deal with snow and sand and grass? What are the things that are limiting our control? And sometimes it's not just the control, sometimes it's the mechanics. So here's the bipedal robot going through barefoot, and in a second what you're going to see is they actually put shoes on the robot, because there's the mechanical effect of actually providing a little bit of stability. It's the same as taking snowshoes out on the snow. It adds a mechanical bit of stability, so the controller doesn't have to provide that passive stability. We can do this in the laboratory if you don't want to take it out in the real world. Here's an example of uneven terrain treadmill that Sasha Voloshina, one of my grad students, built a number of years ago so that we can study human locomotion on uneven terrain. It's possible, you just have to be creative in the ways that you design your experiments. This is a more recent version of it. So now we're studying brain dynamics, cortical activation while you walk on uneven terrain. And what we're doing is using a range of gradations of different types of treadmill surfaces. So by printing out these hard foam discs and velcroing on treadmills, we can manipulate the unevenness levels to basically do a dose effect. When you make the surface more and more uneven, how is the brain responding? How are the mechanics responding? What are the ways that we adjust? How do you change that in a controller for an exoskeleton? Obstacles and unpredictable obstacles. How do you deal with that? We have a recent paper by Andrew Norden, one of my postdocs, that showed that you can actually look at the brain dynamics and the mechanical response when you have these unexpected obstacles. If you don't want to do it out in the real world, you can actually just cover up the front of the treadmill and drop obstacles off the front. This works, and these are the types of experiments that we need to start getting at if you want to evaluate the agility in the real world of exoskeletons. So then how do we get at embodiment, and what do I really mean by embodiment? This is a concept that's been around a long time in cognitive neuroscience and psychology, mostly in terms of tool use. How do you take a hammer, or how do you take a drill, and you use it as if it's a tool, so it's an external device, or do experts become really well versed and do they embody it and take it on? The same could be said with passive prostheses. The more that individuals use passive prostheses, there's more the likelihood that they could adopt it into their body schema. So I borrowed this graph from Rasso et al. From a review paper in 2015. I thought it really produces a good idea that you have internally inside of your nervous system a representation of your body schema. What are the different parts of your body, from the head and the trunk and the arms and the eyes and the pelvis and the legs? And then you have external things. You have the ground, you have force fields like gravity, you have external targets, you have individuals, objects, you have constraints, everything external to your body schema. And usually when we think about using tools, they are outside this body schema. When we use prostheses, most of the literature suggests they really are outside this body schema. And what we need to do is get to the point where exoskeletons and powered prostheses are actually adopted within that body schema. They're seen as a representation within our nervous system, so that they're not an external agent with constraints and forces, but that we have control over them and that they are part of our body schema. And this is really important given all the work that has happened over the years about internal models of motor control. Anytime an individual has a desired motion that they want to produce, they have internally within their nervous system an inverse model of all the equations of how their body works or how they think it works. They send the desired motion through this inverse model. That gives them the electrical signals that they should send to their muscles, which then produce the motion, and then sensory feedback comes back through afferents and peripheral pathways. There is also a forward model. So when we have our inverse model and we deduce what electrical signals we need to send to our muscles, that goes through an afferents copy to a forward model of the way our body performs. They predict the sensory feedback. You do a comparison of the actual sensory feedback with the predicted sensory feedback, and then you can update your inverse model. This is a really nice concept for understanding how we are using exoskeletons, because in an ideal way, prosthetics and exoskeletons should be just a variation of this inverse model and forward model within our brain. If we know how this device works, it's very predictable, then we can adopt it into the body schema and we can send the right electrical signals to our muscles to get the motions and have the right anticipated sensory feedback. So how does this work in action? One example, Stephanie Wong, a PhD student of mine, worked on developing a EMG-controlled lower limb prostheses a number of years ago. The way we did it is we actually took electrodes and mounted them inside the socket of a lower limb prosthesis so that we could record the muscles in the residual limb. So these muscles still produce electrical signals. If you ask them to pull their toes up or push their toes down for an amputee, they can generally, the vast majority of them can produce some electrical signals to those muscles. Now it turns out if you actually measure the electrical signals they send to their muscles while they're walking with their passive prosthesis, it no longer looks like the electrical signals they used to send when they were physically intact. And we've shown that in some publications, but they can learn and they can adjust how they recruit these muscles. And so when you actually devise a controller that takes these electrical signals and controls a prosthesis, in this case, generation 1 was just the pneumatically powered lower limb prosthesis with dorsiflexors and plantar flexors. Pneumatics is not great for being portable, but it actually works quite well in that it produces a natural compliance, which your muscles and tendons normally have. And so it's a pretty safe way to interact and test in a laboratory. And when you do this, it actually works quite well. So here's an example of one of our subjects who is controlling this lower limb prosthesis. She's a transtibial amputee. She has no left foot. She's learning to push off on her toes. She can control it and move in a way that she likes. She then practices walking on a treadmill with it, and over time she adapts the muscle activation patterns that control that lower limb prosthesis. We did this with 5 subjects. We trained them for a fair bit of time, and it was actually quite powerful to listen to the way they talked about the prosthesis over time. So over time, they started saying things like, I haven't seen my ankle move in 10 years. And we had to tell them, no, it's really not your ankle. But they were starting to adopt it into their body schema because they were sending electrical signals from their brain to their spinal cord to their muscles that were controlling it and seeing real-time reactions. And you're right, they do not have proprioceptive feedback. There are no sensors on the prosthesis that go back to the human, but they do have cutaneous sensors in their skin. They have all their normal proprioceptive abilities above the amputation that allow them to sense how those actuators on the prosthesis cause their body to move. And so they actually do develop this internal closed loop control where they're getting information about how their body is moving in relation to how they activate the muscles. The next generation is not pneumatic, it's electromechanical. So Nicole Stafford, a PhD student in my lab, is working on making this a portable device using some actuators from Apptronic, which is a spin-off company in Texas, from University of Texas. And it's working quite well so far. And we're definitely finding that the amputees are adjusting over time. And it's not a time scale of minutes or hours. It seems to be a time scale of days and weeks that it takes for them to practice to relearn how to activate those muscles to use them for control. So, again, to reemphasize Megan Huber's question about, what needs to be happening, I think we really need to focus a little bit more on the agility and the embodiment of how human-machine interactions occur. And with that, I want to give a shout out to the Cybathlon, which is coming up, hopefully. It won't be canceled. Started by ETH Zurich. I think it's a great example of it's not just so much a focus on energy cost with lower limb prostheses and exoskeletons, but they're actually looking at the agility levels. They're actually looking at how well they can perform tasks. And once we get a higher awareness in the field in terms of how important these other domains are, it will really help us take a better look at how we're designing the devices and how we're going to make them improve in the future. So with that, I'll just thank the people that did a lot of the work. These are grad students, postdocs in my lab, and the funding sources. Thanks for listening.
Thanks, Daniel. Really interesting. We received a couple of questions, but we don't have time for all, so let's go with one. So Murad, for example, says, some works about muscle fatigue distinguish central fatigue from peripheral fatigue. Do you plan to separate your assessments according to this separation?
So I would say that's a really interesting question that has relevance, because one of the things we find with the amputees is that they experience what I would term central fatigue in trying to activate the muscles to control the prosthesis. It's not so much that they are metabolically challenged by using the prosthesis, but the mental attention and the ability to devote the awareness to activate the muscles becomes very fatiguing on them. And so it's not really at the level of the muscle metabolites as much as it is the central fatigue. And I would say that's something that's going to come into play as you try to use myoelectric control for peripheral devices.
Okay, probably we have time for one more question. Shuzi asks, would different placement of EMG sensors affect the final performance of the proportional myoelectric control?
It definitely affects the level of control. So we take a fair bit of time to figure out where the best location is on amputees, because you don't know where the surgeon has placed the muscles and how they've tied off the muscles once they've done the surgery. But once you figure out the best location, it seems to be pretty consistent across multiple days and weeks. And so generally we take pictures of where the electrodes are placed, and if you can get them remotely in the same place in future days, it works just as well.
Okay, let's thank again Daniel for the presentation with a virtual applause.
Can I ask another question? Can I ask just a quick one? So because at the beginning I was very interested in like the survey of all the measures that we can use for evaluating exoskeletons, and I'm very interested into the metabolic one, but applied to outdoor use or real case use. Like in the lab, we can use like the VO2 mask for measuring oxygen consumption, for example. But if you were to use like choose or suggest surrogate measures for measures on the field where you cannot, I mean, equip people with masks, what would you suggest?
So number one, there are lots of masks that are possible in the field, and we've used them and they're fine. If you don't have the money to buy a portable mask, I would say heart rate's a pretty good indicator. As long as you keep them aerobic and not anaerobic, then the heart rate pretty much scales linearly under most circumstances. And we've never seen any examples of comparing heart rate and metabolic cost in the field if they're aerobic trying to do locomotion, where there's not a really good relationship.
Okay, and have you ever tested them in very like stressful conditions?
Yeah, and so we've done climbing stairs in a stadium. So that's one of the recent things we're working on right now, is looking at exoskeletons.
Climbing stairs in stadium?
Yeah.
So okay, like a heavy exercise.
Yes, and okay. The heart rate seems like it works pretty well too.
Okay. Okay, thanks.